All right, I think we're about to start. So welcome everyone to the first afternoon session of TyDe'. We're about to hear 4 talks, all very interesting extended abstracts for this year's TyDe'. And the first one is Ayumu Saito, who will tell us how to define a intrinsically typed probabilistic programming language within a theorem prover. Ayumu.
Okay. Thank you. I would like to talk about an intrinsically typed probabilistic programming language in Coq. First, I explain about motivation and contribution. Our first motivation is symbolic evaluation of probabilistic programs. For the sake of explanation, consider an example. This example means that whether today is a weekend or weekday based on the number of buses passing by. The program involves several key steps. First, sampling whether it's a weekend or weekday using Bernoulli distribution. Next, setting the number of buses passing by during 1 hour based on the value of x. In the weekend, 3, and in weekday is 10. Next, evaluating the likelihood of observing 4 buses passing by, assuming a Poisson distribution. Finally, normalizing to ensure probability sum to 1. The issue here is how we can formally prove that this program corresponds to the intended distribution shown in the slide. Our second motivation is the proof of transformation of probabilistic programs. Consider the commutativity of let-in expressions. This lemma shows that swapping the first and second line of the code does not change the meaning. This equation holds under the condition that x is not free in E2 and that y is not free in E1. This is a non-trivial property relying on Fubini's theorem for S-finite measures. The issue is how to turn this property into a formal lemma. About these motivations, we made the following contributions. We provide a formalization of SFPPL. SFPPL is a first-order probabilistic programming language, and its semantics uses S-finite kernels. Kernels are essentially functions that return measures. And S-finite kernel is a class of kernels. And S-finite kernels have a good property of being stable by composition. This stability is used to give a semantics of let-in expressions. More specifically, in this presentation, we make 3 technical contributions. First, we provide an intrinsically typed syntax using canonical structures and custom entries. Next, we introduce a denotational semantics for SFPPL. Finally, we demonstrate practical applications in symbolic evaluation and program transformation. First, about intrinsically typed syntax in Coq. For the sake of simplicity, we will temporarily introduce a language focused on the basic element of functional language called a toy language. The type is U for unit and R for real number. The expressions is element of type U, R for real number, X for variables, plus operator for addition operations for only real numbers, and let bindings. And the context is defined as list with list, not as a set. Then the typing rules is here. TT is for the element of type U. R should be real numbers. The variable X is variable X is typed to the type that is paired with the first X in the context. Addition for only real number. In Latin expression, the environment is extended by X typed in A. We formalize the basic types U and R as an inductive type and define a context as a list of pairs of a string and of a type. With intrinsically type syntax, the expressions are defined by an inductive type, indexed by a context and a type. Basically, it is defined according to type rules. The lookup in the variable expression is a function to find the type of X that first appeared in the context. A lookup is computed when you take a ground string. We encounter an issue when encoding expression like this code. The problem arises when we try to construct such expressions using the inductive type. Inductive type without an explicit intermediate context. We need to give outermost context. We do not give a type because it is intrinsically typed. We expect Coq to compute the intermediate context using the proof of equality E level. Unfortunately, the abstract syntax tree does not type check. Example and error message are shown on slide. Looking at error message, it looks like Coq does not exploit all the available information. We solve this problem by improving unification using canonical structures following Gonsier. There is some boilerplate. First, we define a structure that incorporates a tagged context and a proof of the unification problem we want to solve between a context and a type. We define a aliases for tags to control the search of a solution. Coq will first look for a solution with a found tag, and it fails, it will backtrack for definition and look again for solution with a recurse tag. Last, we declare canonical instances for the unification problem. Found tag corresponds to a variable at the head of context. Recurse tag corresponds to a variable in the tail of the context. We show in the next slide how to use this boilerplate. Redefine a variable expression with a fine structure instead of a context and a proof of equality. For fine structure f, context of f is the first projection, a context, and context proof f proof f is the second projection and equation. Sorry. Example letting out is fixed as follows. We use x bar prime instead of x bar. We put a 4 instead of e level. 4. This 4 will trigger unification. The structure is automatically inferred and put in place of the whole. Next, I talk about the syntax and semantics of SFPPL. First, I show complete syntax of SFPPL. About types in addition to the type of toy language. Type B for bool, type PA for distribution over A, and product type. The expression defines the necessary constructors and gives a distinction between deterministic and probabilistic. Similar to toy language, context and type as indices. The distinction between the deterministic and probabilistic is managed by a flag index. We illustrate the syntax with constructors for probabilistic expressions. We display informal typing rule and its encoding. Sample is a probabilistic expression. It is encoded by type XPGT. Its parameter is a deterministic expression. It is encoded by the type XDGProbT. We see that the syntax encoding embeds the typing rule. The encoding of score is similar to sample, except that it is an expression of type unit taking as parameter an expression of type real. The encoding of normalize is like sample but other around. It takes a probabilistic expression and returns a deterministic one. The semantics for type R is the measurable space for reals, taken from the mass comp analysis library. And the semantics of the Cartesian product A1 times A2 is the product of measurable spaces, also taken from mass comp analysis. And semantics of PA is the set of probability measures with an appropriate generated sigma algebra. The semantics of context is an iterated product. The last U is for unit when context is empty. Semantics of deterministic expression and context gamma with type A are measurable functions from the semantics of gamma to semantics of A. And semantics of probability expressions are S-finite kernels. Next, we consider formalizing the relationship between syntax and semantics. Functions correspond to deterministic expressions are defined as deterministic values, and S-finite kernels correspond to probabilistic expressions are defined as probabilistic values. We describe the relationship using mutual inductive. For deterministic, come with a proof that the function is measurable. For example, let us look at evaluation of variables and return. The semantics of the variable expression is essentially a function that accesses the environment to retrieve the corresponding value. First, we compute the index of the string variable in the context G. Archetype is a generic measurable function that accesses the environment appropriately. Measurable archetype is the proof that archetype is indeed measurable. The relation between the syntax return E and the semantics let us assume that E evaluates to a function f where let f is the Dirac S-finite kernel corresponding to f built using the Dirac measure. In practice, it is desirable to define it as a function rather than as a relation. So we prove the properties of left totality and right uniqueness. By using left totality, we were able to define exec D and exec P. As function exec P as functions that return measurable function and S-finite kernels. Exec D is shown here. A measurable function is a dependent pair of the function and a proof that it is measurable. Next, by using right uniqueness, it is possible to prove that exec D has the same correspondence as evil D. And it is guaranteed that it behaves correctly as an evaluation function. Next, application example. Staten's birth example shown in the first slide could now be described as this. We use custom entries here for readability. We want to prove that the execution of this syntax is equal to the intended probability measure. Exec p let in transpose transposes syntactic let-in into notation using semantic let-in. This let-in, semantic let-in. And since the let-in expression appears 3 times, it can be applied 3 times xp let-in, like this. Next, exec sample can be similarly rewritten. By repeatedly rewriting the exec expression, we were able to transform it into a semantic form. Applying semantic rewriting rules finally is such a measure. Here, \d stands for the Dirac measure. Finally, conclusion. We propose an approach to intrinsically typed syntax in Coq using canonical structure and custom entries, and denotational semantics for probabilistic programming language, and for formal reasoning about probabilistic programs. Please see this link about future work. So, especially contribute to mass comp analysis to support more distributions. Yes, thank you.
All right, thank you very much, Ayumu. We have time for maybe one quick question. Yes, Pierre, let me.
So a quick question then. There was some trouble with defining the tags, differentiating the tags. Why not use de Bruijn indices instead of having to deal with strings and canonical structures? Oh, that's fine. If it was just a design choice like that, that's fine. Just curiosity.
Sorry, I have no idea.
That's fine. We can take it offline. Don't worry.
What do you mean?
So all the x's and the y's that you have to do the canonical structure to find them in context.
But even with the Bruijn indices, you will still need to go to the context to find the tag corresponding to the index.
Mm-hmm.
So maybe it's moving from strings to natural number indices won't change the thing that the is not solved.
Okay.
The mapping between string and indices, it's maybe here regarding
Okay. Okay. Thanks.
All right, let's take the discussion of, precise discussion of representation offline. I will be interested in looking at that too. So let's thank Ayumu again.